Our next speaker will be Professor Luís Pereira from UNINOVA, and he'll present sustainable large area electronics on paper, challenge, opportunities, and applications. So it is okay, just muted.
Sorry, I was here trying to figure out what was going on wrong.
Everything is fine now.
Okay, so thank you very much. Good afternoon, everyone. So I will here present some concepts related with the implementation of large area electronics on paper, starting by the challenges that need to be solved. And it's nice to be the last one speaking because some of the things were already addressed related with materials and processes, but I will stress out maybe some other questions that are not immediately seen or considered when we try to develop devices on paper by printing technologies. And then I will focus on some real world applications. And here I will basically also switch some hats that I have because I'm here talking from the research work that we developed at UNINOVA and Nova University Lisbon. But also I will speak about how some of these concepts can be translated in industry products, talking with my other hat of CTO of Collaborative Laboratory Alma Science. So you'll see kind of change in the even in the slides template when I reach that point of the applications. But okay, starting from the outline and of course the motivation. So the motivation, and we have been talking about that already. So it's how to make more sustainable and responsible electronics. And one of the main goal is considering that if we want to create this type of devices and new type of devices on large area, we need to consider that we should not contribute to the problem that already exists regarding the electronic waste. So we all know these figures. I guess we don't need really to go through it. So it's kind of impressive values that with the most recent reports show the amount of e-waste generated. So it's increasing every year. And maybe looking to the picture on the right, even if it refers already to 2019, I guess the main problem is that around one fifth of it is recovered, and all the rest is just wasted. And when we waste this, we also waste the value of the materials that are used to process these devices. And so we have not only the problem of the waste generated, we have the problem that is not properly handled in the end of life, because some of these devices are not even designed to be considered as reusable or be possible to recover. And also the value that is wasted in terms of money and cost of the materials that are used. And so when we go for sustainable electronics or responsible electronics, I used to say that we need to consider here three main vectors. And these vectors are related with the use of abundant and environmental friendly materials, are the use of also low energy demanding processes. And this has to do also with not only the selection of the process, but also the time that we need to process these materials or to deposit these materials. So it's also relevant. It's not only a question of the process, it's also the question of the time that the process takes. And also think on the end of life, so how we can reuse, recycle, or recover the materials that are used. Okay, so these are the three main vectors that I used to say must be looked at when considering here the development of new electronic devices on large area, because we are also talking about large area. We are talking about generating also large area e-trash. And so I will focus a little bit on this first part, on the most scientific approach and the basic research approach. And I will talk a lot about zinc oxide, that is a very versatile material that are used in many applications, but I will focus on the application on transistors and sensors. and also the use of an abundant material that we all know, the most abundant polymer in the world, in our planet, it's the cellulose, and how we can use this wonderful material not only as a substrate when you consider paper, but also as a material with some more novel functions on these devices. And so I will start the first part of my presentation looking at the challenges and opportunity offered by paper and printed electronics. And so if we consider printed, of course, we need to consider different techniques to deposit functional materials on the substrate. And let's focus here on paper, but we have already heard about other substrates. But also consider that some of the other substrates, when you go for a large area, disposable or transient electronics, polymers are also not an option. Because if you generate, and I will talk about a real world application, if you generate square meters of garbage, electronic garbage of plastic, you are not solving any problem. So focus on the printing technique. So there are many options to deposit functional materials on paper. And if you consider, for instance, transistors, that is the basic unit for electronic circuits, not only the active material is relevant and the conductive one, but typically the most challenge, I used to say, that is also common for or it also true for the common transistors. It's the dielectric. I used to say if the semiconductor is the heart of a transistor, the dielectric is the brain because controls the transistor itself. So and people normally do not pay much attention to these. They stick a lot to the printing the semiconductor layer. And this is the trickiest part, I would say, because to print a good dielectric that is good insulator, it's not easy. And so some other concepts include the using of electrolyte gating that solves some of the issues, and I will go back to that later, but also introduce some problems. That is the eye switching delay, so that will affect the maximum frequency that you can operate these devices. And also introduce large parasitic capacitance that has the same effect on the switching speed. And so it presents nice properties, but also has relevant drawbacks when you are implementing these concepts. And here I bring a work indeed from Emmanuel that is here coordinating this webinar to say what is the approaches of making printable layers on top of flexible substrates. So you can start from a precursor, a liquid precursor, and deposit it, and then convert it on the oxide material, for instance, that you need to make an oxide semiconductor transistor. It's a very elegant way. So many works have been published around it, how to decrease the temperature by combining different approaches. But at the end, you still need temperature. You still need another source like UV light or a laser to help it. And sometimes you also need time. And so the time can also be from 10 minutes, for instance. But even if you consider 10 minutes in the roll-to-roll process, it's a huge time. And so you have another opportunity. So instead of converting a material, you can start already from the material itself. So let's go back to the zinc oxide and the oxide semiconductor. So you can start from zinc oxide already. So do not need to convert a precursor into zinc oxide. You start from zinc oxide nanoparticles, and you need to deposit. Okay, here the challenge is another one, because you need to ensure that you will form a continuous film, ensuring also a proper percolation between the particles when they are printed or assembled on the substrate. And there are several strategies also to do that, also playing with very elegant manner like chemical sintering. There are also something that we already tried and works nicely, but it's not exactly easy to implement in a roll-to-roll process, that is electrical field sintering. And you can also use some binders that help you to get this percolation. So there are many options. And indeed, it's a good approach because you can deposit the particles and you can just dry it very fast in a roll-to-roll machine, seconds in a convection air furnace, and it's perfectly compatible to the printing process. I will start by showing some concepts on where we use the paper itself as a gate dielectric. So we start working with this long time ago, more than I would say 1 decade ago, exploring how to tune the paper properties to operate as a gate dielectric. So it works either as a substrate and as a dielectric in device. And here you have the structure of a transistor where you have to deposit a semiconductor layer on top of the let's just put here the laser pointer. So on top of the substrate, you need to deposit a source and drain contacts that can be metal or carbon. Here we have focused a lot on the oxide semiconductors. And on the back, we have the gate electrode that can also be a TCO or a metal or carbon. So, we have different options for these electrodes. And let's start by thinking on the semiconductor layer made of zinc oxide nanoparticles. And so, as I mentioned, you need to be sure that you ensure you get the percolation path for these particles. So you need to have a certain concentration of particles to allow it. Okay, so, and of course, the critical part is the contact between the particles, because it's the highest resistance introduced in the system is exactly coming from this interparticle contact. So you see here, by making a kind of frequency analysis, you see that the value of the resistance of each particle is much lower than the resistance that you can get from interfacial between the particles. And so that is the critical point that governs the percolation of charges. And so we see here, for instance, that if you just put the particles on the top of the substrate, you may have to rely on the contact points they made. But you have also another approach that we developed some years ago that is to fill these spaces, indeed here playing with the mixture of zinc oxide nanoparticles with a precursor. But I already mentioned that the precursor may be a problem due to the temperatures and the time required. And here, what we played with was to a very low temperature for curing and very fast curing, 5 minutes and 80 degrees to cure this precursor. We don't need indeed to get the perfect or I would say a very performing zinc oxide thin film resulting from the precursor. We just need it to fill the gaps and to improve the percolation. And indeed, you can see that you can reduce by 1 order of magnitude the impedance of a film when you go from this approach to having also the precursor resulting in zinc oxide in between the particles. This is also another effect that keeps the particles together that will have some problems in staying in the substrate if you just deposit them on top of a paper substrate. So this has a double effect and results very nicely, because you see here that we developed an ink made of zinc oxide nanoparticles with zinc nitrate, and we have EHMT, and we made an ink that could be placed in a pen, and that you can indeed write over a substrate, a paper substrate. And you see here how the layer results. And we tested on paper dielectrics, okay, starting from, at that time, a conventional paper. And as I mentioned, so you have the particles over the paper, and when you put this precursor, basically you create a layer that glues the particles to the substrate and keep the particles together. And what happens is that the paper itself can work as electrolyte, a very bad electrolyte, but works as electrolyte, solid-state electrolyte. And when you put a positive voltage at the gate, you displace ions, you create the electrical double layers, you accumulate electrons on the surface, on the interface between the paper and the particles. In this case, also in the film of the zinc oxide that results from the precursor, and you can create a channel. And you can modulate also the depletion layer that exists around the particles. And so you can have devices like a transistor working in this very bad, I would say, performance, but you can already demonstrate that you can make modulation of current, even with requiring high voltage, and you see a high hysteresis. Okay. We have demonstrated this also UV sensors if you don't operate the gate, and if you connect some resistors, you can demonstrate some inverters. But the most important point is that we have demonstrated that you can modulate it and without requiring high annealing temperatures or high, let's say, or long processing time. We also developed some specific paper substrates that as I've said, in this case, are working also as a dielectric. So based on nanofibrillated cellulose that we can dope with different ions, so make a kind of ion doping to improve the ionic conductivity of the paper substrates. And you see here how you can really improve the performance, reducing strongly the hysteresis, but most importantly, reducing the operation voltage by 1 order of magnitude. So just also the optimization of the dielectric itself introduces here a huge improvement on the performance of the devices. So we can reach mobilities on these films that surpasses 15 square centimeter per volt per second. But we can also do another thing, that is, okay, so instead of using the paper itself as a dielectric, you can develop specific electrolytes also made of cellulose that can be used on transistors and replace the paper as a dielectric. So we also developed this, so made from cellulose derivatives. And the idea was that also, this is just a curiosity, of course, they can be also self-healing. They present self-healing properties. So if you damage, they can recover the mechanical properties and keep, okay, more or less keep you see the variation. So keep ionic conductivity always close or above 1 millisiemens per square centimeter. That is perfectly enough for this application. We can make it with lithium only. We can mix with sodium ions as well. And the most important thing is that they present high capacitance. But if you look to these, you can already start already to understand which is more or less the maximum theoretical frequency, operation frequency that you can extract from devices using these electrolyte. Because you see that you have a big drop on the electrical double layer capacitance when you increase the frequency. And so you see that around 1 kilohertz to 10 kilohertz will be more or less where we have a big drop and these devices will no longer operate. And this is already in optimal conditions because it also depends on the dimension of the devices. Still going on, so you start by printing the contacts. Here we are printing the source and drain contacts and the gate contacts because these are planar transistors. In between, you print the zinc oxide layer, and then you put on top of the device connecting the channel and the gate electrode, you put these electrolytes. So basically, this is the architecture of the device. You have the 3 electrodes now on the same plane. The paper is the substrate. The semiconductor layer is in between, and you have the dielectric, the dielectric or the electrolyte in this case, connecting the channel region to the gate. And you see here a real photo of the device, and you see also the SEM micrographs of the surface after printing the zinc oxide layer before putting the dielectric. So this is the paper, this is the after printing the electron carbons, and this is the paper coated with the zinc oxide layer. Another thing that you can do is also play with the shape of the particles. So we are using spherical or close to spherical zinc oxide nanoparticles, but you can also go for nanoplatings. So you can also synthesize zinc nanoplates by playing with hydrothermal synthesis of these plates. And what are the advantages is that, yeah. And you can use either spherical and the nanoplates, and the ink itself that we are developing, or that we developed, is based on the mixture of carboxymethyl cellulose and zinc oxide, either the nanoplates or the nanospheres. In this case, you see the nanospheres, but you see also the concentration of zinc oxide nanoparticles that you need to add to the ink in order to get the proper surface coverage. And so the results, the best results, and the results that I presented so far is with 40% weight percentage in the CMC ink. Okay, and you see that with that, we can even get low impedance at room temperature without requiring further annealing after printing and ensuring proper percolation. So it's a very important point because, as I mentioned, so you don't need to heat, you just need to dry the water that is the solvent of the CMC. That can be done in the convection oven on roll on the web. And so you see here the office paper with the particles now printed, and on top we have the dielectric. I put here the silver gate electrode. You saw before that is not indeed the architecture of the device, but I put it here, the gate, just to show what happens when you put a voltage on the gate. So basically you push positive ions from the gate to the surface of the nanoparticles, and you are changing the depletion layer that exists on the surface of the particles resulting from the defects and you are creating a conductive path around the surface of the particles. One advantage of using electrolytes is that you can get a better coverage also around the surface of the particles. So not relying only on the contact between the particles and the dielectric. And so this nicely results also in devices operating at very low voltages with on-off ratios very convenient and mobilities around 20 square centimeters per volt per second. Of course, and we talked about that already, some of the previous speakers, these are intended to be flexible, and it's one of the drawbacks of these films made of nanoparticles is when you start to bend it. And interestingly, they behave differently if you are bending inward or outward, as you see here. And I will put here a picture just for you to understand. So what happens when it is in the flat state, when you bend inward and when you bend outward? You see that inward, it's much more, let's say, dramatic for the film made of nanoparticles than the outward bending. And so this is an issue that we need to deal with. And to minimize it, or to try to minimize it, we went for an approach where the ink, instead of being made of spherical zinc oxide nanoparticles, we use nanoplates of zinc oxide nanoparticles. And so basically, during printing, they tend to assemble over each other. Again, we have the problem of the contact between the nanoplates, so everything will be determined by the contact to ensure the percolation. But as they assemble over each other, even when they are submitted to a stress, so when you bend, you are basically putting a tensile stress on the surface of the substrate. When you bend inwards, you put a compressive stress. When you put outwards, you put a strain. And indeed, this strain, what we observe is that in some cases could be indeed beneficial, because if you put a tensile strain, you may force a better alignment and assembly of these of these nanoplates. And you see here now the benefits comparing the inward to the outward. So when you put a compressive stress on these particles or when you put a tensile stress on these particles. And you see that the films, in this case here, resist much better when they are made of nanoplates to the outward bending. And we have demonstrated some other device, some logic gates can be demonstrated NAND, NOR, and NOT gates. So it's just the way you connect the devices. So if you have just one transistor and one resistor, if you have two transistors and one resistor in series, or if you have two transistors in parallel with one resistor. So you can make different types of logic gates, just connecting the transistors through the carbon conductive paths. So this is really nice. So it's just a demonstration of the concept. You can also sorry, let me just see if I can start the movie. Yeah, I'll put the movie going on. You can also recycle basically these, because you can go and chop these circuits made on paper, and you can make recycling paper. In the movie, you will see this. Maybe I need to just to speed up a little bit the movie, because just to change here to turn on the. So here we are just removing the electrolytes. You can recover the electrolyte, so this is interesting because you can dissolve it. Okay, again. You can recover it, make new membranes by just casting it and let it dry. So you have new electrolytic membranes that you can reuse. And concerning the paper, you can chop it, of course, and make new paper from out of it. So of course, the carbon and the zinc oxide nanoparticles will be incorporated on the recycled paper in this case. But the membranes themselves, they can present similar electrochemical behavior after being recovered and reshaped again in new membranes. And if you use them in transistors, they can make, let's say, working transistors again. Okay, so these are really nice concepts that we try to develop to solve some of the challenges and so opening new opportunities for some materials and devices. But when it goes too close to the market, we have to have a new approach. And now I will put the head of CTO of this collab, Alma Science. Uh, that is a innovation lab. So that is a lab that has dedicated research to take these ideas and concepts from research to real products. Okay, and so we focused, of course, on the sustainable technologies because I'm talking about sustainable electronics. And one of our, I would say, technical bundles are focused on the, two of them, sorry, are focused on electronics on paper. One, I will talk about the two options for the two bundles. One is related with pressure sensors that can be implemented on paper substrates. Another one is related with RF tags that can also be implemented on paper. So Alma Science has two offices, one in Lisbon, and some facilities also shared with university, and also let's say dedicated facilities in Lisbon, and also in Aveiro, in the center north of Portugal, where I also have shared facilities with another associate. That is the Research Center for Paper and Forest, Raiz, that is part of Navigator company, that is the biggest paper making in Europe. And indeed, so those are some of the associates of what we call the Smart Paper Incubator, where we have also sold the official printer of the documents in Portugal. And we have a paper converter and a company related with biotech, and then many then commercial partners that are also engaging with our activities. But maybe what is relevant is to mention that, okay, if you think about transient electronics and sustainable electronics, so you need to think on the materials. We already addressed this. You need to think on eco-friendly production. Of course, the time and the cost of production is very, very relevant. But you also need to think on some business value. And that's where the critical part is, because you need to be pragmatic on selecting what indeed from all these nice things we do at academia have indeed application in real world. And of course, this is just transversal. So to be focused that these technologies should be somehow not creating, I would say, eco-friendly as well. And so I bring here two selected technologies and the approach that we have followed, and the pragmatic approaches that I said that I used to say that we have followed to try to bring some solutions on paper, large area electronic solutions on paper to the market. And the first one is indeed a very mature technology already inside the Alma Science Collab. We call it Paperweight AI. It's already a spin-off. So it's a company that you can then visit the website and offer solutions for retail, so monitoring of shelf events in retail. And so it's basically a paper-based pressure sensor that is aimed to retail stock monitoring that can be applied, of course, in other areas than retail, but the use case specifically and the spin-off was starting around applications in retail. It has limitations because it can count products and not indeed identify it yet, but we are reaching that point, but I will explain how we are reaching that point later. So basically, just to frame, you need really to be pragmatic to see, okay, so I want to implement large area electronics. I know that I have limitations if I want to make very complex circuits on paper using printing technology. So what can I do indeed that is useful to be implemented in large area, that is cost effective, that will have acceptance by the market, and what I cannot do, and that is still in the infancy, or the performance will never reach that, or that will create more problems than solve. So that is indeed where the equilibrium point is the market acceptance and what really makes sense to do. And in this case, of course, I guess, and I'll be back to that later as well in my conclusions, we need to be pragmatic and we need to follow at this moment kind of what we call it any hybrid approach. That is to simplify what you put and print on the paper that is still good enough, as the previous speaker mentioned, and what you need to transfer to the outside using conventional electronics. that are, of course, much more performant to make what is required when connected to these paper devices. And so I will not enter in details about the fabrication of these sensors because of the trade secret. Sorry, it's under patenting. But just to say that is a lamination of two pieces of paper with fully printed. So we have a printed electrodes, two different materials, one metal and carbon. So we are trying to go fully carbon-based, but still until now was not possible. And also a piezo-ionic layer that is made of cellulose as well. So going out of what was already also discussed from the conventional PVDF materials. So all the materials are either carbon, metal ink, or the rest is everything is cellulose, the sensing layer and also the substrates, of course. And here is the starting point. So we had the surface layers. We need to develop the electronics to connect. I must say that one critical point, and so sometimes we never consider these things, but the critical point was to develop the connector, the mechanical connections from the hardware electronics to the hardware on paper. So it's very tough to develop a proper connection that would resist, and I will show another slide later why this is important. And of course, just to say that we are working with the sensing, the pressure sensing, to figure out let's say the occupancy of an area. And just again to remember that to be good enough, also the resolution of these surfaces had to be optimized to the conventional dimension of objects in retail. So you don't need millimeter resolution for this application. You need centimeter, and I'm saying centimeters resolution for this specific application. So again, understanding the market, understanding the needs, and tune the product for the right needs will be the secret to find some applications. And of course, nowadays, we know that we have this powerful tool of computer science, more known as artificial intelligence, even if artificial intelligence nowadays is also used to merge many concepts that sometimes are not simple as that. But just to say, of course, that we have these powerful computing tools nowadays. And again, you can simplify your matrix. You just need to train it to recognize different classes of products and also train the system to understand if you have the same number of products where they are located in order to understand the shelf occupancy. And so just to mention that another critical point to bring these things to the market nowadays is to understand the right tools that you need to combine to make a viable product. And again, you see here a video, how it works. I'm reaching to the end, Emmanuel, so do not worry. I know that I'm ready. Okay, so this is not working, but just to show how the system is trained and how it can count objects. And this is already under test in real environment with 3 retailers, one big retailer in Portugal and 2 small retailers, one in Portugal and one in Germany. And we are about to start another proof of concept with another big retailer in Portugal in May. You see here the dimension of this surface nowadays. So they are customized to the typical dimension of shelves. And you see here assembling these on the shelf, and then the connection, and what you don't see here would be on the video. So, but these videos are on the server, and I don't know, they are not running properly. But it's a rail with the connections to the surface, and this is just a protection that is used to not to damage, especially with water or liquids, the sensing surface. Even if the surface needs to be replaced, this protection can be reused, and so this will not generate any extra waste unless it gets damaged as well, of course. And again, so just to say the dimensions is adjustable to the dimension of the shelf, and this can be produced in roll-to-roll, and it's already being produced in roll-to-roll with a partner in Finland to make these proof of concepts where we are covering already hundreds of meters of shelves with this solution. So this has been already, as I said, a company, a startup, now raising the first funding, first round of funding. And this is just recent participation in the retail fair in New York. And another solution that I will not spend too much time on it because it's still not at the same level, but is the creation of RFID tags that can be implemented in every object. So, and for that, you need really to further reduce the cost considering the conventional RFID technologies. And we are betting on what we call chipless RFID. So it's RFID tags without chip, without the silicon chip. So that can be used for identification and for sensing, and it can goes up to 50 centimeters reading distance. So you don't need a chip, but that comes with some drawbacks. So the conventional technologies offer a high capacity of codification that is not possible with this technology. But for low number of serialization, so low number of codes that you maybe require, or even for sensing, it's our focus because the cost is the cost of a print. So we are talking about less than 1 cent, sub-cent costs for these tags. And this can be implemented in every object, including every piece of fruit that you have in the supermarket, that is the concept I showed before. And so, again, this is a combination of hardcore electronics with dummy electronics going on the paper substrates in order to reduce the cost and make it, let's say, interesting from the operational point of view. And basically, here is another video to demonstrate. So you can put objects, these tags, as I said, in objects like an apple. You see the tag that can be directly attached to an apple. Here is a tag on the chocolate box that will identify then the object when you put it over the reader. So the system will identify that you have, in this case, the chocolate box. And if you replace again by the apple, you see the system will identify the apple. So these are made directly on paper by printing. You can even print it directly on cardboard. And so it's an advantage also over conventional RFID chips that you cannot do these in every packaging material that you can consider. So it's an advantage, even considering its limitations. So just to wrap up, so the challenges are on the development of functional materials, the performance of the devices that they have when they are printed on paper, specifically on paper, that is even a kind of, let's say, challenging substrate and surface. The opportunities are on the applications that you can think on the materials that are sustainable, like the cellulose or those based on zinc oxide, where you can use it in real world applications. So and even the processes that you use, how they can be adapted and modified to real world applications. Scalability, it's also a big issue. Okay, so you can have the most wonderful the material or the most wonderful device. If it's not scalable, it will never reach the market. And for having applications, so the strategy so far needs to realize in simplification of the technology implemented on paper substrates, combining with hybrid electronics, transferring the complexity to conventional electronic systems. And of course, nowadays we have a powerful tool that is the computing capacity and the algorithms that are helping to turn what we call it dumb electronics in smart electronics. So, and this is indeed a key enabler for real world applications. And so thank you all for attending, and I would like to thank to the both teams that, let's say, contributed to this, so from the research part and also from the tech transfer part. So thank you very much.
Thank you very much, Luís, for the amazing talk. You can see here the future of paper electronics. It went from the materials and device level to some real application. I think is quite interesting from the community. So I don't know if exists any questions here in the audience. I have a question. So you mentioned that one really important part was the connector to so how is it? How did you solve the process to have a good connector with your wearables based on paper?
Yeah, it's indeed something that you don't think, or is not the first thing you think about when you're trying to develop, because okay, I need to print a good conductive layer, I need to print a good sensing layer, then I need to laminate, and at a certain point you understand, okay, now I need to connect this to an electronic port, and you make the first connections, and after some time, after assembling the first samples, you realize that they start to break because paper is not plastic, so you can easily or more easily break than plastic. And so we had to make a kind of first mechanical clamping to the paper in different points to spread the stress that is applied to the paper, so through multiple points. That was the first strategy. And then when you go for application on the shelves, to create kind of a buzz line um, that connects to these connectors in order not to have wires hanging, because the wires hanging is where you can accidentally touch and create some extra tension. So it was a kind of already a product development phase where you need really to understand what would be the best approach to solve the issue for this specific application.
Yeah, thank you. And in the end, you speak about a really important thing that was scalability. So we need to prove that it's scalable. But the other really important point that you show two products is to have necessity in the society to have it. So even everything connected to print electronics and devices that are not so complex, we need a requirement about billions of devices. And you show some possibilities that have these requirements. And I think that is quite important to show. So this shipless FID, even the one in the shelters. So if you see in the large view, I think is that the way to go.
Yeah,
Right?
it's where which the need comes from exactly when you have also volume. Okay, so you can have really nice printed electronic stuff, but you don't have volume. It will be always expensive and maybe not attractive to be developed. In this specific application, if you think that you need to, just in a one supermarket, you have more than, I would say, 1 kilometer, a very small one. You have more than 1 kilometer of shelves. So it's where it starts to make sense to have a kind of cost-effective solution to apply. It could be done in plastic, of course. It could be more or less the same price. It's not a question of price of the substrate, even if paper can be more competitive in some cases, but depending on the plastic that you are considering. Of course, if you consider Captain, it's more expensive, but others could be as cheaper. But then when you have this shelf life for these things estimated for 2 years, if you consider that after 2 years you need to replace kilometers of shelves, so you are creating kilometers of plastic waste. While if you do on paper, okay, so you in principle you can even recycle it. Okay, so and here, as I mentioned, so combining with conventional electronics is where you have also an opportunity, because the electronic parts, the brain, I would say, will remain the same. So you don't need to replace it. So it can be reused. So even if you damage one shelf, you can replace just the sensing layer, and the electronic part will stay there. Just to mention also another advantage of this, it's very important, maybe for those that are attending, and sometimes we may not realize exactly or immediately, is that supermarkets don't want to stop for a long time to install these things. So this should be installed overnight. So with the minimum disruption of the activities of the supermarket. So this is also important. You should go with a roll, install it, and the next day is operating. So this has an advantage over more complex systems that involve specific shelves, where you have load sensors on the shelves, but where you need to replace all the shelves that exist in supermarkets. So they don't want that. So uh, also the need comes also from this point. So as I said, so look for the need, and sometimes also the challenges are not immediately visible, or the opportunities are not immediately visible. So depending on the application.
Yeah, exactly. So thank you very much, Luís, for the
Welcome. Thank you for the
great
invitation.
talk. And last, I'd like to thank to everyone here that attended the INFRACHIP Digital School of Sustain, and to all the speakers for your availability and really nice talks. So thank you very much and have a nice day.